Okay, so I want to start off by giving a little bit of motivation and talk about the problem itself at a high level, and then we'll get down and I'll show you the governing equations and what is it that we're trying to invert for, what data do we have, what parameters do we invert for, and how do we go about doing it. So this is the flow of ice from polar ice sheets, and when we say polar ice sheets, we primarily mean Greenland and Antarctica. This is where all the action is. Any melting of the ice in the North Pole, the Arctic ice cap, that does not have any effect on sea level, Archimedes' principle, and the other land ice in the Andes, Alps, Alaska, Himalayan glaciers that are melting are contributing now. These are maybe half of the contribution to sea level rise is coming from those, but in the future it will all be dominated by Greenland and Antarctica. And there's also thermal expansion of the oceans, but that is a small amount, an order of a few millimeters per year, depending, of course, on the temperature increases. So it's the land that's on ice that has the too many caipirinhas last night. It's the ice that's on land that has the potential to increase sea level, and this is a flow process. The ice is flowing off of land into the ocean, and the observations for the last 20 years, satellite observations, indicate that in a number of areas, these ice flows have been increasing rapidly. Okay, at the moment, it's about 200 billion tons per year of ice that's delivered from these ice sheets into the ocean, but the flow rates of a number of outlet glaciers in Antarctica have been increasing over the last several decades. Why this is so, there's questions about it. Could be the warming ocean. There's been increased polar circulation. And the winds that circulate around Antarctica, these have intensified over the last decade. This has led to greater mixing in the polar ocean, which has brought warmer water from below up to the surface, and that interacts with the ice sheet. As the ice sheet flows off of land, it forms an ice shelf, which is floating on the water, and this one can flow unimpeded. There's little friction at the base. And in a sense, these ice shelves act as a sort of buttressing effect. They keep the flow of ice from land from increasing, and as they break up, and there have been a number of recent dramatic breakups of ice shelves, the Larsen B ice shelf in particular, in the Antarctic Peninsula some years ago. So the thinning of the ice shelves, due to increased mixing in the ocean, has brought warmer water to the surface, and this has led to a loss of buttressing effect in the retreat of the ice sheet. But there's also conjecture that this ice is getting underneath, the warmer water is getting underneath the ice sheet that sits on land and lubricating the base. And I'll show you a cross-section through Antarctica. West Antarctica is actually below sea level. That is, the ice is so heavy that it depresses the continent. And so if water can get in underneath, it flows downhill. I'll show a picture of that in a minute. So there's a conservative estimate, now this is called conservative, of half a meter of sea level rise by the year 2070. And this is estimated to jeopardize 136 of the largest port cities with 150 million inhabitants, $35 trillion in assets. So these are projections, they're subject to great uncertainty. But you can imagine if there is a half a meter sea level rise, then Houston is in jeopardy. Bangladesh is in jeopardy, and so on. Clearly, if any kind of policy is going to be enacted based on the predictions of these models, we have to have some way of quantifying the uncertainty of the models. You can't just go to a policymaker and say, well, 0.63 meters of sea level rise is the output of the model. You have to say something about the confidence you have in that. And as we'll see, the Bayesian inverse problem gives one a perfect context in which to study these issues. I want to cite a couple of papers. This one was from last summer, the summer of 2013, in which the authors found evidence for abrupt sea level increase of 5 to 6 meters at the end of the last interglacial period. So just before the last ice age began, 118,000 years ago, they found evidence for rapid increase in sea level. What does rapid mean? Well, how did they find this? They found coral, fossilized coral, at these elevations in Western Australia. And carbon dating the coral, they can put it to from a few hundred to maybe 1,000 years, is that range. So if sea level rose abruptly by 5 to 6 meters over 1,000 years, it's likely that civilization could adapt. Houston would have to be moved inland, that it would take 1,000 years, and that's okay. On the other hand, if it's over 100 years, It's impossible. You can't adapt to that level of sea level rise in 100 years without massive catastrophic changes to civilization. So, of course, this is without human influence. It has nothing to do, increasing CO2 concentrations in the atmosphere have nothing to do with this. This is a natural cycle. And the big question is, what could possibly cause this? What can cause 5 to 6 meters of sea level rise over a relatively short period of time? And the conclusion of this paper is there's only one possible explanation, and that is catastrophic destruction of a portion of an ice sheet, most likely the West Antarctic ice sheet. And this paper now, from this past summer, a few months ago, suggests, controversially, that we are at the beginning of such a period, a collapse of an ice sheet. This may take 1,000 years, but they point, this is based primarily on data, with a little bit of modeling, but mostly on data, and observations of the thinning of the ice sheet in West Antarctica and radar cross-sections, ground-penetrating radar that can see through the ice and look at the base. And as they see the ice sheet retreating in portions of West Antarctica, they can see that there's little, the topography at the base offers little resistance to acceleration of the flow. Not everyone agrees with this, with the finding of this particular paper, but it's controversial. Let me show you one video to plant some notion of what these flows look like. Now, this is not a model. These are from satellite observations, synthetic aperture radar. This gives you the surface velocity of ice in Antarctica. And what you're seeing here, the warmer colors are faster flows. So this red indicates several kilometers per year. Ice is falling at several kilometers per year. And these other colors, this is meters per year. So it looks almost like a mountain range that is being drained. It looks like water flowing down. You have these ice streams, literally ice streams. This particular area we're going to zoom into is a problematic area. This is the Thwaites and the Pine Island and Thwaites Glacier. And this region in particular has been studied for the last 20 years, and these flow rates of these outlet glaciers have been observed to be increasing rapidly. There's thinning of the ice in that region on the order of 60 meters. This is the ice that's on land, has been thinning over the last 20 years. And that area is known as the underbelly, the weak underbelly of Antarctica, is what glaciologists how they refer to it. That area has potential for 6 meters of sea level rise, just the catchment that it drains. If that region destabilizes, if, let's say, the ice shelf breaks up and the ice flows faster, potentially that could lead to 6 meters of sea level rise. All right, there's a quote from the IPCC fourth assessment, the Intergovernmental Panel on Climate Change. This is the last report. There's a new report that is in the various stages of coming out. But this last report, essentially says that ice flow is not included in the current models. And that's true. The 2007 predictions of sea level rise were based purely on thermal expansion of the ocean and a little bit of melting. But what we're talking about in Antarctica is not melting. You can increase temperature significantly. Antarctica won't melt. It's too cold there. What would happen is the oceans warm up, the oceans interact with the ice flows faster off of land, and that's the mechanism. So that's not included in the 2007 report. And the reason it's not included is, in particular, the uncertainties in the land ice models themselves. They threw up their hands. They said, we can't model this process. Too complicated, too many uncertainties. We're going to leave it out. There is an attempt to include it now in the 2014 report. This is the last of these picture slides, I think. Shows you cross-sections through West Antarctica and East Antarctica. This may be a bit hard to see, but the white here that's the ice, and of course the yellow is land. And you can see most of West Antarctica is below sea level. That is, the ice is so, this is sea level, is the black line here. So the ice is so heavy that it has depressed the sediment. This is several kilometers thick. The thickest part of the Antarctic ice sheet is 4 kilometers, extend to several thousand kilometers. So the ice has depressed the land on the order of, it could be hundreds of meters below sea level and even greater, up to a kilometer. And what the fear is that water can get in underneath the ice sheet, lubricate the base of the ice sheet, leading to some sort of dynamic instability. As the ice flows faster, more water can come in and flow underneath and lubricate even deeper parts of the ice as the ice retreats. Okay, so it's a difficult problem to model, and there's a nonlinear rheology, you'll see it in a minute, strain rate dependent rheology. Because of that, you end up with very difficult linear systems to solve numerically. In principle, we'd like to couple with the hydrology beneath the ice sheet, the transport of fluid underneath. We know that the sediment underneath in regions, it's a porous fluid, and there's water flowing around. There are lakes underneath. The geometry is complicated, wide range of length and time scales. But the principal difficulty is the uncertainties, and in particular the basal boundary condition. That is the boundary condition at the base of the ice. We don't know what that is. We can use radar to image through the thickness of the ice to see the topography. So we see the shape of the base, but the boundary condition there can be anything from no slip, where the rock is frozen to the ice, to free slip, where the ice is sliding freely due to lubrication. And the lubrication is occurring because of geothermal heat flux, because of friction that melts some of the ice, and water can flow in from the ocean as well. So this is the primary uncertainty. The topography itself, we have to interpret the radar images, so there's some uncertainty in that. The rheology, we can do experiments on ice in the laboratory, but field ice has some contaminants in it, essentially volcanic eruptions. You can see in the radar cross-sections, you can see layers where different volcanoes erupted over time. But largely that's reasonably under control. The geothermal heat flux, there are models that predict that. We can measure it on a global basis. And knowing the variation locally, there's some uncertainty there. But really the primary one where we have no idea, unless we solve an inverse problem, is the basal boundary condition. Fortunately, we have good observations. Interferometric synthetic aperture radar, which gives us the velocity on the surface. Laser altimetry, which gives us the height. The mass changes due to the GRACE satellite. And we can take ice cores, they're very expensive, but we can do them. And ground penetrating radar, which gives us an image through the thickness, which captures in some sense the deformation history of the ice, because we can see layers due to this volcanic ash. Okay, I'll just take a few minutes and talk about the forward problem. Not much, because I really want to talk about the inverse problem. That's the key issue. The governing equations are simply the usual Balance laws of mass, linear momentum, and energy. The momentum equation is missing the convective term. The Reynolds numbers are negligible. You have a rheology that's temperature and strain rate dependent. And you can see there's an expression for it over here. The energy equation, you have strain heating on the right there, but otherwise things are standard. U is the velocity, P the pressure, epsilon dot the strain rate tensor. Now the rheology, there's a temperature dependence through an Arrhenius type expression, and then there is a strain rate dependence through the second invariant of the strain rate tensor. The first invariant, because it's an incompressible flow, is 0. The third invariant, generally the standard viscometric tests that are done in the laboratory, can't measure it because that turns out to be 0. But it's found that one gets a good fit to data with dependence on the second invariant. And this n is the power that's chosen to be around 3 for ice. So this is taken to be 3, so this is a negative exponent. So it's a shear thinning fluid. And what's happening is ice will flow under dislocation creep, and ice crystals deform and align themselves with the flow, which reduces the effective viscosity. Boundary conditions, there's a dynamic free surface, traction free at the top, and the material derivative of the vertical component matches the accumulation from snow. A is just the annual, the height of snow per year that falls, which varies throughout Antarctica. For us, the critical boundary condition is this one. It's a Robin type boundary condition, so it's a linear relationship between the traction and the velocity. This is simply the tangential operator. So the tangential component of the traction balances the tangential component of velocity through this parameter beta, which is referred to by glaciologists as the basal sliding parameter. Sometimes they call it basal friction. It's not real friction, but it represents a resistance to flow, tangential flow. So if beta is infinite, then the tangential component of velocity is 0. So you get a no-slip boundary condition. If beta is 0, then you have traction free in the tangential direction, and the normal component is 0. So beta is the uncertain field, and we're going to invert for that from the data. And that's generally a very highly heterogeneous field. It can vary over 8 or 9 orders of magnitude. We know that just by solving the inverse problem. Okay, so I'm not going to say much about the discretization of the forward problem. The only thing to be said is that it's critical because we're going to be solving this problem over and over, thousands of times, tens of thousands of times to solve the inverse problems. We better have a good forward solver. And we can talk about the issues, but I'd rather skip them. I'll mention a few. We need to have adaptive mesh refinement working well because this region, for example, this is where the ice leaves land and becomes an ice shelf, it floats on the ocean. So there's a change in boundary condition there. So in principle, there's a singularity. And one needs a very fine mesh to resolve the so-called grounding line. And then one can have a very coarse mesh in the interior, and then finer near the grounding line and other regions. I should mention these ice streams as well. Let me go back. You have these regions where the ice is flowing at several kilometers per year, and next to it, the ice is moving at meters per year, tens of meters per year. So it's a huge contrast, 3 orders of magnitude contrast in velocity. So we need a fine mesh to resolve these regions, these margins of these ice streams. And these ice streams are simply, it's like a river carving out a basin, coming down a mountain. So these ice streams get carved out, and there's sort of a dynamic feedback where the flow velocity increases due to increased shear stresses at the base, the driving shear stresses at the base. Okay, so so some of the issues we need high-order discretization, and we actually need to conserve mass at the element level. With this kind of rheology, standard finite element approximations, that incur mass losses at the element level, don't work very well. Quickly, you accumulate errors, and you get very poor solutions. So you need to design finite element methods that will conserve mass at the element level. We need to be insensitive to the aspect ratio. There's a very high aspect ratio. There's 1,000 to 1 type of aspect ratio geometry. The solver has all kinds of issues. You'll see there's an effective anisotropy that emerges. When you linearize this rheology, what you get is a fourth order effective anisotropic viscosity, a tensor. And I'll show you that, and particularly the adjoint equation. When you do this linearization, that pops up. You need to be able to handle that in your solver. There's very large heterogeneity, both in the sliding coefficient, which can vary by 9 orders of magnitude, and in the effective viscosity of ice. Viscosity of ice is about 10 to the 13th Pascal seconds, so 16 orders of magnitude more than that of water. Okay, so we put together. I'm going to skip over these things. If anyone's interested, I will share slides. Just to give you a sense of how well these solvers work, because they're the critical component of the overall scheme, you can look at scaling. You can increase the problem size from 38 million unknowns to 2.1 billion unknowns. Ultimately, these are the sort of target problems we'd like to solve that have 100-meter resolution at the grounding line and perhaps a few kilometers resolution interior. But they lead to very large problems. And what you see is that the algorithmic complexity of the method is optimal or near optimal. That is, as you increase the problem size and you go to larger numbers of processors, the number of Newton iterations remains constant, solving the nonlinear equations. The number of Krylov iterations remains, it increases by a factor of 2, which is quite good for 2 orders of magnitude increase in problem size. So this is about as good as we can do. We've thrown all the technology we can at this problem, exotic discretizations and exotic preconditioners and solvers, and everything you can think of. And so this part is okay. What's not okay is the parallel efficiency. That is, the mathematical qualities of the algorithm are near optimal, but the performance, especially when you get to 100,000 processor cores, it falls down and you have 42% efficiency, for example. So that remains a challenge, and simply because manufacturers are building supercomputers that we can't compute with. They've run out of, it's been about 10 years now that clock speed has stalled. They can't make the clock speed of the processors any faster. They just consume too much energy and they generate too much heat. So they're just cramming more and more cores. Everyone knows this. Every generation of machine you buy has double the number of cores in the previous one. And our algorithms are memory bandwidth. They're sparse matrix algorithms. They don't map well onto these high throughput type devices that are perfect for high school kids playing video games. So this is what's happened, and we have to live with it. So we essentially have to reinvent the way we discretize and solve PDEs of computational science in order to keep the 14-year-old video gamers happy. Okay, so let's skip that and let's go directly to the inverse problem. So first, I'm going to talk about the classical approach to the inverse problem, the regularization type of approach. And this is, this is sort of our starting point. And this is how I used to approach inverse problems until I became a Bayesian. Okay, so this is the classical formulation of an inverse problem. We have data. In this case, this is observed surface velocities at the top of the ice sheet from satellite data. So it's an entire map of the surface velocity. And use the velocity of ice, which depends on this parameter, this coefficient, in a Robin boundary condition, which is uncertain. So it's in red. We're going to invert for it. B is just an observation operator. So it extracts the velocity throughout the ice. It extracts the surface velocity. All right, so we're comparing the surface velocity predicted by the model with that observed in some L2 sense. This could be weighted. And then this is an ill-posed inverse problem. I will show you numerical results to verify this. One can prove ill-posedness for simpler problems, but with this complicated ice sheet with the nonlinear constitutive law, we can't formally prove it, but we certainly compute, and you can see eigenvalues decay to zero, and I'll show you more about that in a sense. So the problem is ill-posed. The data do not determine this field, beta, uniquely. When you discretize beta, we'll have 500,000 or 1,000,000 parameters. They're not uniquely determined by the data. And so we add a regularization which essentially annihilates small length scale components of this beta field. It puts a large penalty on the oscillatory components of beta. So this is simply the tangential component of the gradient. When you take the first variation of this, you get the Laplace-Beltrami operator, so sort of a diffusion operator on the topography, on the basal topography. Okay, so that's our objective function, and we solve this, and our method of choice, the gold standard is Newton's method, which involves a Hessian operator acting in a direction beta tilde is equal to minus the gradient. So the question, of course, is how do we compute the gradient and the Hessian? And our approach is, as continuum mechanicists, we use the classical Lagrangian formulation. We use the governing nonlinear Stokes equations as constraints. Variational calculus, you turn the crank and you work it out on paper and pencil, and then you discretize everything. So you take variations, form Hessian and gradient expressions, and then discretize, and that's the standard approach that we take. And you can update the field in this fashion. So the gradient, if you go through this process of forming the Lagrangian, taking variations, the first variation gives you the gradient, which looks like this. So it's a very simple expression. This Laplace-Beltrami operator comes from the regularization, and from this term over here, one gets simply that the tangential component of the velocity, the inner product of that with the tangential component of an adjoint velocity, and I'll show you the adjoint equation in a second. This forms the gradient, and so we're trying to drive the gradient to zero. The exponential of beta here simply comes because we've reparameterized the problem so that the beta represents the log of the sliding coefficient because it varies over 9 orders of magnitude. Okay, so that's the gradient, and what does the green variable, which is the adjoint equation, that comes from this adjoint Stokes equation. So here's the forward Stokes equation, which is nonlinear. The adjoint equation is linear in the adjoint variable, v. It resembles the Stokes equation. You have divergence of the stress and mass conservation here. But the right-hand side is different, so that this free surface boundary condition, rather than being traction-free, this is now driven by the misfit between the observed velocity and that predicted by the forward model, the blue coming from the forward model here. What's interesting is that the stress tensor here has an anisotropic relationship to the strain tensor. So this effective viscosity now there's an isotropic component, but then there's an anisotropic component taken by the outer product of these two strain rate tensors. So when n is 1, this term drops out, and you have, with linear rheology, you don't get this effect, but with nonlinear rheology, when you linearize, you do get this fourth order effective anisotropy, which is acting in these second order directions. Okay, so that's the adjoint equation. Yeah. Yes.
How sensitive are your results to
Which one is alpha the? Oh, the regularization parameter. Yeah. So what I will show you is that the most informative modes the data give you the best information on relatively smooth modes of the beta field. So if you choose alpha correctly, and I'll show you, we have a procedure for choosing alpha, the L curve, which is standard in inverse models. If you choose it correctly, you can annihilate the oscillatory modes which the data don't inform, but retain the modes that the data is informing. Now this takes some iterative procedure. So the answer is, if you do it correctly, it should be insensitive. I mean, the result will be sensitive, but the information contained in the data is not polluted by the regularization if you're careful to cut things off at the right place. Yes?
Before you get back to where you came from, can you say a little more about this observation of Praia?
Oh, this is just a symbolic. This simply extracts from the velocity everywhere. It extracts. Yeah.
That is your function, so
Yeah.
that must have a mathematical form. Or it's only numerical.
Yeah. No. I mean, it's just it's simply the velocity at the surface. This simply means the velocity at the surface. That's all it means. Yeah. Yeah. Now, if it were point-wise observations, as you have many inverse problems where you measure at a point, then that would have delta functions in it. And then we'd have problems with delta functions, we'd have to mollify them in. Yeah. But here it's just the surface velocity. Okay, so now the gradient is fine, but that's not enough. We also need the Hessian acting in a direction. The Hessian itself cannot be computed. It's a dense operator. Every column of the Hessian corresponds to solving the forward problem once. The Hessian is of order of the number of parameters. We have 500,000 or 1,000,000 parameters, beta parameters. So we would have to solve the forward problem 500,000 times. That's out of the question. So, however, what we can do is we can form the action of the Hessian in a direction, and it turns out to have this expression. If you just go through if you apply the Lagrangian formalism one more time, then you can derive this expression. It looks very much like the gradient expression. There are a few extra terms, and the extra terms come from the magenta variable, which is this u hat, and that's from solving an incremental forward equation, and then this orange variable, which is the incremental adjoint. So it's a second order adjoint, sometimes these are called. But the equations that are solved resemble those of the Stokes equation. It's the same operator on the left-hand side, same anisotropic fourth order tensor viscosity, and just different right-hand sides. So again, it's just paper and pencil work to get these. This is that was the incremental forward, this is the incremental adjoint equation. So at the cost of solving two linearized nonlinear Stokes equations, we can form the action of the Hessian in a direction. Now you say, how does that help me? Because, don't I have to solve this system to find the update? And well, what we do is we use conjugate gradients, which does not require the Hessian by itself, it requires its action in a direction, and these matrix vector multiplies can be done on the fly. And one gets good performance. Okay, and just to show you evidence of that, we don't want to dwell on this too much, but here is an increasing number of parameters. This is a synthetic inverse problem, not using real data, so we know the true answer, we can terminate it appropriately. Number of parameters going from 10,000 to 1.5 million, state degrees of freedom to 22 million, and the number of Newton iterations is essentially constant. Number of conjugate gradient iterations is essentially constant. There's a reason why these are constant. I'll say more about that later. So we're happy that we have a scalable method. On the other hand, you're still solving several thousand Stokes equations. So it is, and when each solution is many thousand processors on a parallel machine, that can get expensive. Okay, so let's go to some synthetic inversions first. And these have 400,000 inversion parameters. So the base of the ice sheet is discretized, that the beta field is discretized with 400,000 parameters. Okay, this is synthetic, first of all. So what does synthetic means? We postulate a basal sliding parameter field. We regard this as the truth. We made this up, and we have some good informed ideas behind it, but we postulate this as the basal sliding parameter field beta, and then we generate surface data from this. So we solve the forward problem, we extract the surface velocities. These are, I guess I should mention, these are three-dimensional models. So the meshing, I showed you a top view of a mesh, but these are three-dimensional models. So this is the surface velocity that we extract from the 3D nonlinear Stokes equation, and then we add noise to it, in this case just 1% noise, to simulate satellite data error. And then we throw this away. We throw the basal sliding field away, and we say, all right, given the data, can we go backwards through the equations, through this inverse procedure and determine the basal sliding field. And here's what we get. We solve the inverse problem using the method I just discussed, and that's what we get. So if you look at the right picture, there's certainly a difference between these two. This is, again, the truth, the so-called truth, and this is what we infer from solving the inverse problem. And there are differences. On the other hand, if you look at the left, so this is the solution of the inverse problem. The left image is the surface velocity field that corresponds to this basal sliding parameter field. So if you notice on the left, there's very little difference between, in fact, there's just a few pixels difference in the observed or synthesized surface velocity and the reconstructed. So that tells you this is evidence of ill-posedness. You have two different basal sliding parameter fields that both give you the same surface velocity. Okay, well, that's life when you deal with ill-posed inverse problems. But the inverse solver has done what it was told to do. It said match the prediction of the model with the data. It did it, and unfortunately, it did not recover the true solution. However, if you look closely, the high velocity contrast regions, which tend to be the regions that people care about, these ice streams, the fast-flowing ice streams, these are resolved quite well, in the inverse solution. So where you have large velocity gradients, that seems to be highly informative about the basal parameter field, and that you can get from the data. And it's these regions in the interior where the ice is flowing very slowly and where the velocity gradients are very low, that those are non-informative. Those tend to be non-informative, but generally those are of lower interest. Okay, so that's a mix of good and bad news. And in fact, let me show you a video of the iterations. These are the iterations of the inverse solver, and you see quickly that these regions underneath the ice streams, within a few iterations, they are resolved. These are the remaining iterations of the inverse solver, and there's a larger number of iterations where the interior is being polished, changed slightly, but it's really these fields within a few iterations are nailed down. Okay, so now let's go to real data. This real data set comes from satellite measurements over the period 2007 to 2009, and this is the aggregate data from satellites from half a dozen countries. So this group synthesized all these together, 900 different satellite tracks, 3,000 orbits, put together that surface image. The video that you saw in the beginning, that's essentially this data set that was being animated, visualized. So it's a velocity at the surface. We assume we're in a steady state here. We assume the velocity is a steady state. This shows how the regularization parameter is selected. This is what's known as the Curve Criterion, where one is trying to balance. As you reduce the regularization parameter, you can provide a better fit. So this is the regularization parameter being reduced. You can provide a better fit to data. This is a measure of the misfit between prediction and observed data. But what happens is the magnitude of the regularized term, that is the roughness in the beta coefficient, that increases rapidly. And so you try to find an elbow of this curve, and it's a heuristic. It's a heuristic, but it's a popular technique for choosing the regularization parameter, which tries to balance the additional difficulty and ill-posedness in solving the inverse problem with matching the data. Okay, because we don't know the true solution here, so we can't just tune this coefficient in order to match the known truth. Okay, so these are using the satellite data. So INSAR data, this is the observed satellite data. We solve the inverse problem, this is what we obtain. Now, I can't compare this to anything. I don't know this basal sliding field. I don't know the true field. Of course, these are phenomenological. That Robin boundary condition is a phenomenological condition. It subsumes complex sub-basal processes. So this beta is really it's an effective parameter. But nevertheless, we obtain this field. And what this field shows us, rather remarkably, is that these weak regions, so this is beta that's very small. Remember, very small beta represents almost, 1 here represents almost traction-free. In the limit, when it goes to 0, there's no resistance to sliding. And then notice this is also the cube root for plotting purposes, for visualization purposes. We took the cube root of this basal friction. So it's really 9 orders of magnitude variation instead of 3 orders in beta. And we plot this, so we see these regions of low resistance to sliding extending deep into the interior. Now, are these real? Are they an artifact of the inversion? Well, this is what the inversion, this is what the data are telling us filtered through the model. So the combination of the model and the data tell us this, but do we believe it or not? Well, that requires sort of understanding and analyzing the uncertainty in the solution. But this is what we get. Now, one question we can ask is, how well did we reproduce the observed surface velocities? These observed surface velocities, this solution, how well does it reproduce this? And that's the next slide here. So if you take this basal parameter field, solve the forward equation, extract the surface velocity, you get this. This is the reconstructed ice surface velocity, and this is the original one. So this is the observed, reconstructed, observed, reconstructed. And unlike the synthetic problem, where we're able to match the surface data almost perfectly, with real observations, you have model error. The real ice doesn't care about your nonlinear Stokes equation. So what happens is we don't get a perfect match, because although we get a reasonably good match, and what we care about, again, is these regions of fast-flowing ice, these regions where, for example, we zoomed in here in this previous, in the video earlier on, into that region where where there's an increased, observations of increased flow. So those regions, we tend to match the surface observations quite well. It's in the interior where the ice is flowing slowly that we don't do as well. So this is another perspective. This is the observed, and this is the reconstructed. Observed, reconstructed. So the kilometers per year flows are matched very well. It's the meters per year, or tens of meters per year. The difference between the light blue and the dark blue, those we're not able to match as well. But again, we have this notion that it's because the surface velocity gradients are small in these regions, and they don't provide enough information. Yes, Victor? Yeah. Yeah. Good question. No, I mean, unfortunately, we don't process. We don't have access to the raw data. We rely on these observational glaciologists who are taking this data and processing it. And so that one data set we have access to is a synthesis of satellite data over the period 2007 to 2009. But glaciologists view this period we're in right now as a relatively stable period. If it were, if we're emerging from the Little Ice Age in the 1600s or going back to the end of the last ice age, these periods of massive change, that's a different story. But for 2 years in a relatively stable time, they believe that a steady state is a reasonable approximation. Now, if we're trying to predict what will happen 100 years from now, with scenarios of doubling or tripling CO2 concentration, potentially warmer oceans, then you have to then this steady state model is no good. But to solve the inverse problem, obtain this beta field, a steady state approximation we think is valid, and the glaciologists we work with say it's a good approximation. But then you have to turn around to a time-dependent, a model that allows a free boundary, and then predict how the ice will change to an increasing ocean, but using this boundary condition that we just obtained here through the inversion. Okay, so here is this shows the errors in the satellite observations. So this is from that data set, and you can see the errors on the order of meters per year. So in a sense, our inability to match the surface data to within a few meters per year, up to 10 meters per year, is of the order of the observational error. So you could say we've matched the data to within the error, and that's good news. And these are just a few zoom-ins, and I'm going to skip over these. This is let's go look at one of them. Let's say this is the Pine Island region. That's the region that the video zoomed in on, the Pine Island and Thwaites glaciers. Again, this area has seen, this back here has seen significant thinning over the last 20 years. And so this is the basal sliding parameter field underneath that we obtained. The left is the observed data, and now that's the reconstructed. So reconstructed, observed, and again, we're fitting the observed data relatively well in the fast flow regions and less well in the slow flow regions. But again, the difference is light blue to dark blue, so on the order of 10 meters per year flow rates. Okay, so this is all fine. We get these solutions, but then we ask ourselves, what do these mean? What kind of confidence do we have in these solutions? And that leads us to the Bayesian approach. So I'm going to give a little bit of a high-level overview of the Bayesian approach to the inverse problem with apologies to those who have a background in this area. So the Bayesian approach has three components. One comes to this problem with some prior notion, so these are probability, each of these is a probability density, and we come to the problem with some notion of what these model parameters M. So here we're referring to the model parameters generically as M. So what these model parameters M should be. And the same thing goes for the observables D. So this is the actual noise in the observation. There's the uncertainty in the observation. So this cartoon here illustrates the components. Suppose I have a single model parameter and a single observable, surface velocity, and this basal sliding parameter. This probability density function here represents the prior knowledge we have of this model parameter. If we don't have any knowledge, it might be just a uniform PDF. But this says that, well, we think, based on past understanding, we believe that this is the mean, and there's some uncertainty in our belief representing the model parameter. And of course, this would have to be at every point. This would be a joint probability density when we do this in high dimensions. And then we we take a measurement, let's say satellite observation, we measure this value, but there's some uncertainty in the measurement itself. Together, these two form a joint probability density. They're independent of each other, so this is simply the product of the two. The third component is where the model comes in. So this represents this third component, and this is the mapping from the model parameter to the output prediction of surface velocity, the observable. This is through the solution of that nonlinear Stokes equation with the strain rate dependent rheology. So this would be a line if it were a deterministic model. In fact, in our case, this is a deterministic model. But the framework accommodates a stochastic model. Stochastic model meaning for a single model parameter, you have a range of outputs. In this case, without loss of generality, this is being assumed, or this is depicted as a Gaussian in the output, and of course these two are Gaussians as well. So the Bayesian approach to the inverse problem takes the conjunction of these two states of probability, produces the so-called posterior, and this is in the data and model space. Of course, what we care about is the model parameters. We're trying to infer those. So we integrate out, that's what this integral here is. So we integrate out where we marginalize the data component, and what we end up with is this probability density here. Despite the fact that we had Gaussian prior and observational densities, we end up with a non-Gaussian posterior probability density for the model parameter, reflecting the nonlinearity of the parameter to observable map, the nonlinearity of the forward problem. So a Bayesian would tell you that this is the solution of the inverse problem. Not a single point here, but an entire probability density, representing the family of solutions that are consistent with the data, taking into account the noise in the data, and consistent with any prior notion of the model parameters, and consistent with uncertainty in the model, if you can build in the uncertainty in the model as well. So this is the solution to the inverse problem. In one dimension, no problem, you draw a picture of it, you can take the mean and higher moments, you can just compute these. In 400,000 dimensions, or 1 million dimensions, what do you do with this? How do you get your hands around? You can't compute the mean in 1 million dimensions, at least formally by integration. Even Monte Carlo integration, you can't, because every point on this surface requires a solution of a forward model. And I'll show you that explicitly. If you, let's see, I think I'll skip this, but I just want to point out that this depiction is for finite dimensional model parameters. When you get into an infinite dimensional model parameter field, which, this is a field, beta is a field, so you have now the beta, the inverse parameter, is now viewed as a random variable, a random field, and what does it mean to have a probability density in infinite dimensions? And so there's been a lot of recent work by Andrew Stewart in particular and others on trying to understand the infinite dimensional framework for the Bayesian inverse problem, and there are a number of issues here that in the interest of time I'll skip over. But you have to, what's important is you have to get you have to define the prior operator to be sufficiently smoothing such that the posterior probability density makes sense, such that the Bayesian inverse problem is well posed. You have to have a sufficiently smoothing prior for reasons that I can talk about later, and then you have to discretize this thing properly. But let's say we've discretized, we're in finite dimensions now. The posterior will look like this. If you have Gaussian Gaussian prior and Gaussian noise, which are two common choices, then the posterior looks like this, which is simply that the posterior probability density, again, this is a solution of the inverse problem, probability density in the model parameters. There's a data misfit component. This is simply the parameter to observable map. So just symbolically, this means go solve the nonlinear Stokes equations, extract the surface velocity, compare it with what you observed, but it's weighted by the noise covariance. And then there is a term coming from the prior which acts like the regularization of the previous deterministic expression. So as someone who's worked on deterministic inverse problems, I look at these Bayesian inverse formulations and I say, oh, these are connected. There's a strong connection. Now, it's tempting to look at this and say, oh, this is Gaussian. However, f of m is generally nonlinear in M. That is the map from model parameters, the beta coefficient, the Robin boundary condition, to the surface velocity through the solution of the Stokes equation. That's a nonlinear map. And so this is non-Gaussian. So the question, of course, is, all right, well, so I have an expression. I can write it down. That's fantastic. But what do I do with it? Well, I'd like to, let's say, compute the mean and covariance in higher moments. In a million dimensions, I can't do it. Every evaluation of this posterior probability density requires solving the forward problem. That is, for some given model parameter field, solve the nonlinear Stokes equation. And that's out of the question. So what the modern approach is, which has totally revolutionized Bayesian statistics, and now is responsible for everything from filtering your spam in your inbox to making decisions at large corporations about strategy and so on, is this Markov chain Monte Carlo method. So Markov chain Monte Carlo replaces probability density with a set of samples, and then we can compute sample statistics, sample means, sample covariance, and so on. So the question, of course, is how do you get these samples? This comes from a Markov chain, and the basic algorithm is trivial. It's almost trivial. It's beautiful in its simplicity. So you start with some point, and what we do is we come up with a proposal density, and this is the crux of the algorithm. You come up with a proposal which you can sample from, but the hope is that it matches the underlying target probability density. So I'd like to come up with some proposal density that looks like this, at least locally, and I can draw a sample from. And then what I do is I compute this ratio here. And if you look at just the black letters here, this is simply the probability of the proposed point over the probability of the current point. It's actually weighted by the forward and reverse proposal density for reason. And if you compute this ratio, if this ratio is greater than 1, then you accept this proposed point. So you propose a point, and if the ratio is greater than 1, that is, if the probability of the new point is greater than the probability of the old point, you move to that new point. Why? Well, we'd like to sample the more probable points. On the other hand, if this ratio is less than 1, again, weighted, if it's less than 1, well, you still have a probability of accepting this point. Why? Because you want to sample the lower probability points as well, but you just don't want to sample them very often. Okay, so if you do things this way, you're guaranteed to converge. Now, how many steps it takes, different story altogether, but if you take enough Markov chain Monte Carlo samples, those samples will converge let's say, in the mean to the true underlying probability density. In practice, this can, even in just a modest number of dimensions, 50, 100, this can take hundreds of thousands or millions of samples, particularly if your target density is complicated. Okay, so what we do here is I'm going to illustrate an idea that comes from the deterministic inverse problem, and then I'll just show you a few results and we'll be done. But first I want to contrast a standard Gaussian random walk. So if you download an MCMC code from the web and you run it in default mode, this is what it would do. Unfortunately, you can't see there are gray contours back here. Can you make those out? This is a target density. It's a banana-shaped, it's called Rosenbrock's function. Suppose we're in 2 dimensions, and we're trying to sample this banana-shaped density, which is actually a difficult density to sample. What the Gaussian random walk would do, this would be the proposal, the blue. As you can see, it has nothing to do, it's a very poor approximation of the underlying density, which has these narrow contours. So if you draw a proposal from this is what the proposal looks like. It's simply a Gaussian, isotropic Gaussian. You draw a proposal from the density that these blue contours show. Chances are it's going to have much lower probability than the target density, and chances are you reject it. So you've just wasted a nonlinear Stokes solve, which is 3, 4, 5 minutes on 4,000 processors. Now, instead, what we'd like to do is come up with a a proposal density that resembles the underlying target density. But the target density of 500,000 parameters, well, what does it look like? So here's what we can do. First of all, if we look at the form of this proposal density, you recognize, first of all, that if we try to maximize this, what we end up with is the so-called maximum a posteriori point. That's the equivalent of minimizing the negative log of the argument, which is simply, which looks a lot like a deterministic inverse problem, except it's weighted by the noise covariance, inverse of the noise covariance, and the confidence we have in the prior model parameters. And so this is an appropriately weighted deterministic inverse problem. But moreover, if we linearize f of m, that's the map from model parameters to output observables. If we linearize those, the posterior covariance is simply given by the inverse of the Hessian, that Hessian operator that we saw earlier that played a critical role in that Newton solver for the inverse problem. So the posterior covariance can be approximated by the Hessian, which I showed you the infinite dimensional expressions for that involves, the action of the Hessian involves a incremental forward and incremental adjoint Stokes solve. So that's great. And this is what the proposal looks like. Again, sorry, you can't see the gray contours at the back, but we're trying to sample the banana function back here, and we have this as a proposal. In fact, at the current point, the blue contours match the gray contours to two derivatives locally. And then, of course, they start to differ when you get out far enough. So the idea is you build a local proposal based on these variational expressions that were formed through the Lagrangian, based on the Hessian. The proposal density has the Hessian in there as a weighting. We call this a stochastic Newton's method because it has essentially the new point is essentially the old point. There is a Hessian inverse gradient term which looks like Newton's method. So that's the direction from the current point to the mode here. And then finally the contours are distorted by the inverse of the Hessian, which approximates the covariance. Yes?
Here, the Hessian is, and the gradients are calculated for the map or for each MK?
Good question, good question. So the gradients in the Hessian are calculated for each MK. I'll get to that in a second, actually. That's an important issue. Okay, so now how does it compare? If you look at the number of samples here at the bottom, this is a model problem, 65 parameters. This is a toy problem. 65 parameters. This is the number of samples, which this is 250,000. You can't read this, but it says 2.5 times 10 to the fifth. Huge number of samples. And this is a measure of convergence. Let's not worry about which measure of convergence. These are all indicators. These are all indicators of convergence. They're a number that Bayesian statisticians use. The black curve is a delayed rejection adaptive metropolis. It's a very popular MCMC method. You can download it from the web and run it. It's actually quite good. And this is its performance. The convergence is indicated by a value of 1 of this measure. And this is after 100,000 samples, we killed it. It wasn't, it was proceeding very slowly. The stochastic Newton method that I've talked about is the red curve. I mean, you almost cannot see this. It's lying right on top of the vertical axis. There is a red curve there. Within a few hundred samples, it samples the target density. Now, I show this to statisticians, and they say, well, you're cheating. You're using these second derivatives. We don't have access to those. And my argument is, well, exactly. Yes, we should be bringing in the structure of the problem. And in particular, this Hessian operator is telling us the important directions. It's telling us the data are informing the model parameters in these directions well, and other directions poorly. And that gives us a distortion. And in high dimensions, that's absolutely critical. Okay, so I'm running out of time. To get to this comment over here, this is a bit unfair in the sense that a standard MCMC is simply using function values, whereas we're using Hessian. And I just said that the action of the Hessian in a direction costs 1 forward, 1 adjoint linearized Stokes problem. So computing the Hessian is actually quite expensive. And if you actually had to form the Hessian, forget it. This would not be meaningful. We would not be able to do this. The good news is the Hessian can be viewed as the sum of a data misfit term, which in many problems is a compact operator. And I show you here an eigenvalue spectrum. You can see the eigenvalues collapsing to 0. This is a logarithmic. These are the eigenvalues on the vertical axis. This is logarithmic axis. So you have 8 orders of magnitude decay for the first 4,000 eigenvalues. This is a problem that has 2 meshes, actually. 400,000 parameters, 1.19 million parameters. The curves lie on top of each other. So it tells you that the data misfit portion of the Hessian, this is the linearized forward operator, linearized adjoint operator, these, the eigenvalues collapse rapidly, despite the fact that for this problem you'd expect a lot of information contained in the data. The data are everywhere on the top surface, and we're trying to infer the coefficient of a boundary condition at the bottom surface. And this is just a few kilometers thick, over 1,000 kilometers in extent. We'd expect to have lots of information, but what this analysis of eigenvalues tell us is that you have 8 orders of magnitude reduction in eigenvalues in the first 4,000 modes. There are 4,000 modes that are observable from the data, and the remaining 1.15 million, 1.19 million minus 4,000. Those remaining modes are unobservable. The data don't tell us anything about those, and it's the buyer. So what we do is, at a high level, we simply do a low-rank approximation of this data misfit operator. Now, this is the prior operator, and this acts like a differential operator. So this one you can't do a low-rank approximation. But this first one, you can do a low-rank approximation. So we extract these 4,000 eigenvectors. We use a technique known as randomized SVD, which works beautifully. I can't get into here, but it's a fantastic method that makes use of random directions, and it gives us this reduced subspace in a number of matrix vector multiplies proportional to R, basically. And so we can extract these dominant directions in a number of Stokes solutions proportional to the important dimension, the information dimension, not the apparent dimension. Okay, so let me show you a few samples and then we'll conclude. This shows samples from the prior on the top. So the prior is non-informative. It's simply annihilating the small length scales. That's all the prior tells us. And the posterior here, what you see, the difference, in fact, let me blow these up. So these are different, as I flip through these are different samples from the posterior. And what's shown on the right are the samples from the posterior, and the left is the mean. So the samples from the posterior, they show large variance in the interior, where there's larger uncertainty. And the variability from one sample to the other in the regions where you have fast-flowing ice and large contrast in surface velocity, the variance is much lower. So one can compute statistics of these things. I'm not going to show you those, but you can compute a covariance of the posterior and so on, and quantities that we care about. Okay, so the other thing that I thought would be interesting to show are, I said that the data misfit operator has a collapsing spectrum that looks like this. Again, this is the first 4,000 modes out of 1.19 million or 400,000 that are important, and the remaining portion of the data don't inform. So it's interesting to visualize what are the data telling us about this basal traction field, this basal sliding parameter field. Again, these aren't showing up very well, but this is the first eigenvalue. So I'm going to show you a few, the first eigenfunction. I'm going to show you a few eigenvectors taken from here. This is the first one. The data are most informative about this. You can see it's smooth, but it's certainly localized. It's not a global, it doesn't have global support. So most of the information is this Ross ice shelf area and this region of West Antarctica there. This is the second mode. This is up again in West Antarctica near the Ronnie ice shelf. Third mode goes to East Antarctica. Now you start to see almost like modes of a drum, a vibrating membrane, but that has variable thickness, with some heterogeneous coefficient. And I'm not going to show you 4,000 modes, but as we go into higher modes, 10, 100, 200, 500, 1,000, we start to see small length scale regions emerge. So the data are informative. This is the 4,000th eigenvector. We have a cutoff. I won't talk about it here, but we have a systematic way of determining when the information from the data is small relative to the prior. And you can see the 4,000th where we cut, after this we cut off, we are informing relatively smaller scale values of the field, certainly not down to 100 meter resolution. Okay, so in summary, we can do regularized inversions. They point to weaknesses that stretch deep into the interior of Antarctica, but we need to quantify the uncertainties in these inversions. The Bayesian framework is a nice way of looking at this, but these computations are generally intractable. And so the notion is that we can bring in ideas from deterministic inversion using this Hessian operator, recognizing that the Hessian can be approximated by low-rank approximations because the data are not informative about the entire field. In fact, often informs just a small portion of the field. And I didn't go through any details of this, but the cost can be shown to be independent of the parameter dimension and data dimension as well. We did some problems where we solved the satellite data on finer and finer meshes, but the information content of the Hessian as measured by the dominant spectrum didn't increase, which makes sense. There's only so much information you can get out of the data on the model parameters because they have to go through the solution of this nonlinear Stokes operator, which is a smoothing map from parameters to the model. Okay, but it's still extremely expensive. I mean, 118,000 forward solves. This ate up something like 5 million processor hours. And this is just preliminary stuff on a coarser mesh than we'd like to. So there are a number of open questions. I'll just leave these up. And you can look at these, but there's lots of questions, lots of mathematical questions that need to be answered here. In particular, the biggest one is how do we explore high-dimensional space? And that's really the fundamental question. In general, I think that problem is just not solvable. If you're in a million dimensions, you sort of have to visit every corner of that space if there's something important. But if you can exploit the structure of the problem, if you know something, then that helps you, and how can we better? Hessian is useful, but it tells you locally what the curvature looks like. It doesn't tell me what's happening in that corner of the room. It tells me sort of, well, depending on how big the third derivative is, because it's all Taylor series. Okay, so I'll leave these up. Thank you so much for your attention.